and then comes your tetra and so on. So this is the first classification on the basis of number of halogens. Now, if you are going to classify on another base, that is your compounds containing CX bond in which carbon is sp3 hybridized. So in this you can see we are going to divide this as primary. This is 1 degree halide or primary. If this is connected like this, you can see this will be your secondary 2 degree, and if this carbon is connected with 3 other carbon, then this is your tertiary or 3 degree hydrocarbon. So this is the second classification. Now in this we have another classification, that is allylic halides, which is very important. In this part is also from this. As you can see, the carbon which is connected to X should be sp3 hybridized, and adjacent to this carbon should be doubly bonded. So this is known as allylic halide. That means basically the hybridization of the carbon to which X is connected must be sp3, and the adjacent carbon should be sp2 or doubly bonded. You can take another example of cyclic structure like this. You can see this is your allylic halides, because you can see this is the carbon which is sp3 hybridized, and adjacent to this carbon we have 2 carbon here and here, in which you can see this is doubly bonded, which means sp2. So this part is allylic. Okay, the next is benzylic, and it is also part of this. Benzylic is also part of this. So you can see benzylic has a name which is related to benzene. So this will be your benzene, and this is your X. So as you can see that this is your sp3 hybridized, and connection to this will be your sp2. So this is also benzylic. All I want to say is that the carbon to which X is connected should be sp3, and adjacent carbon should be doubly bonded carbon, that means sp3. Now the next classification is based upon compounds containing CX, and this should be sp2. Now as you can see that means to the carbon which X is connected should be sp2. That means X is connected to the doubly bonded carbon, that is known as vinylic. So you can take another example of this like this. Doubly bonded carbon, that means sp2 carbon X is connected, and another is, we say, aryl halide. That means directly X is connected to the benzene ring. So this is your aryl halide. Is that clear? So this is the basic classification. Saif, Mamuna, Aksa, Hiba, Farhad, Alan, can I change the slide?
Yes, sir.
Yes, sir.
Okay. Now we are going for the nature of CX bond. So this nature of CX bond. So as you know that X is more electronegative than carbon. So on X there will be negative charge, delta negative, and there will be positive charge. That means this bond is basically polar in nature due to the electronegativity difference. Now I am gonna give you polar. This is your polar. Now I'm gonna give you some basic questions. This is your CH3F. This is your CH3Cl. This is your CH3Br. That means alkyl group is same. And this is your CH3I. Now you are going to arrange this A, B, C, D in order of. First, you are going to write in order of bond length. First, you are going to write in order of bond length. Then you are going to write in order of what we say bond enthalpy or bond energy. Bond enthalpy I'm going to write. Then you are going to write order of dipole moment. So if you have revised, you can easily do this. This question is absolutely from NCERT. And I think you can do this. Please do it. Any answer? Okay, let's see. One thing is common in all this, that is CH3. So we are not going to take CH3. Only the difference is they have fluorine, chlorine, bromine, iodine. And as you know that with increase in size, bond length also increases. That means this is the smallest in size. That's why its bond length will be the smallest one. And hence D will be the largest one. D will be the largest one. Then comes your C, then comes your B, then comes your A. Now, when you are going to talk about bond enthalpy, it's very simple. You know that bond enthalpy is inversely proportional to bond length. Bond enthalpy is inversely proportional to bond length. That's why you can see fluorine having the lowest size. So it will have the most bond enthalpy, then A, B, C, and then D. Now come to this dipole moment. You know dipole moment, that is mu is equal to Q into D. This mu depends upon charge as well as distance. Depends upon charge as well as distance. And this charge comes due to electronegativity difference. Electronegativity difference. So as you can see, fluorine is the most electronegative. So it should have most dipole moment. But if you are going to check it, this chlorine will have more dipole moment than fluorine, than bromine, and then iodine. Basically, in dipole moment, generally, your charge difference or electronegativity difference dominant. But in case of chlorine, as you can see, it is electronegative as well as its size is also bigger. That's why chlorine dominant on fluorine, and hence the order is this. Is that clear, everyone?
Yes, sir.
Okay.
Sir, can you repeat the reason again?
See, mu depends upon Q and D. And generally, this mu is totally dependent on electronegativity difference charge. Okay. So as you can see, fluorine is the most electronegative difference. So the charge difference will be more here. Chlorine is also the fourth most electronegative element. Fluorine, oxygen, nitrogen, and then chlorine. So there will be a little slightly little charge than fluorine, but size also matters there. That's why chlorine dominant on fluorine, and you can see here the electronegativity difference in bromine and chlorine carbon is not that much. That's why here down the group basically electronegativity decreases. If you are going to move down the group, electronegativity difference electronegativity decreases. Chlorine dominant on fluorine, that's why this happens. Okay, sir.
Yes, sir.
The next, as you can see, we are going for methods of preparation of haloalkanes. Haloalkanes. And the first method you have studied it in class 11, 12, that is from alcohol. So everyone knows that. Everyone knows that. I'm gonna just write it. As you can see, if you are going to react ROH in the present with HCl in the presence of ZnCl2, you are going to do the reaction ROH in the presence of NaBr and then H2SO4. Then what you will get after this, we have 3 moles of ROH and you are going to react this with PX3. Then what you are going to get here, X will be only for chlorine and bromine. Okay, plus PCl5. Then comes your ROH. If you are going to treat this with red phosphorus in the presence of X2, and here X2 again, Cl2 and Br2. And the last, not the least one, which is very important, ROH plus SOCl2, and it will be equal to R. Now I'm gonna tell you the product. First of all, this reaction will you will be again studying in alcohol chapter, and this is what I want to say. This is Lucas reagent. This is Lucas reagent. What will happen? You can see this is plus, this is minus, this is minus, this is plus. So this plus will go to, wait a minute, please. Chlorine is more electronegative, so negative, and here it will be positive. So negative will go to positive and you will get RCl. Now, if you are going to just change this, you will get RBr. If you are going to react this RX, you will get RX along with H3PO3, along with H3PO3. In here, you will be getting byproduct NaHSO4 along with H2O. We generally don't deal with byproduct. These are main products, but in this and in this, whatever we will get in byproduct, that is also important. So you will be getting RCl along with POCl3 and HCl. So this the byproduct of this both reaction are important. It has been asked so many times. Now you can see RX, you are going to write it RX, and here you can see it is RCl along with SO2 and HCl. You all know about this reaction. All I want to say is that this and this and this is very important. Why this is very important? Because this product, this reaction we prefer to prepare haloalkane. We prefer to prepare haloalkane only because these byproducts are in gaseous state and we get directly the main product RCl. Is that clear, everyone? We prefer
Yes,
this
sir.
reaction. Okay. Now, these star mark reactions are important only because of this byproducts. It has been asked. Now, the most important point is this Lucas reagent, because in this, I'm going to show you a reaction. This is your ROH, and you are going to react this with HCl, and in the presence of ZnCl2, and you will be getting RCl plus H2O. Actually, this reaction proceeds with carbocation, formation of carbocation with carbocation. Basically, its intermediate is carbocation. And whenever in any reaction, carbocation formation takes place as an intermediate, then, wait a minute, please. Then rearrange if possible. Then rearrange if possible. All I want to say is that I'll show you with an example. This is the reaction. If I'm going to write it step by step, see what will happen. First, this alcohol will be terminated. This will be negative and this will be positive. So there will be formation of carbocation. And this OH minus will be going with H plus and forms H2O as a byproduct. Then what will have only, what we have only Cl minus. This will be attacking with each other and then RCl forms. So basically this reaction mechanism, in this reaction mechanism, we have carbocation. Now I'm gonna give you a very good example of this. How the, what we say, how the rearrangement takes place. Basically, if you have this CH3, CH and CH2OH, and if you want to go to react this HCl and ZnCl2, can anyone tell me the name of the product? Please do try. Then I'll tell you. Steph?
Yes, 1 minute.
Aksha, Hiba, Farhat, Alan. Alan, you are not responding at all.
Sir, chlorobutane.
Okay. Okay, let's see. First of all,
Sir, can you
generally
enable chat?
enable chat. Oh, I cannot see chat box here today. Wait a minute. No chat box option. Let me tell them to enable it. You can tell me the answer directly. See, generally what does students do? They remove OH and they add Cl there. That is good. This there is CH2. That was by mistake CH only. And that is good. But this is not the major product. This is not the main product. You know why? See, first of all, I told you, whenever you are going to see this reagent with alcohol, there will be formation of carbocation. That means this OH will be removed. If this OH will be removed, so what will be the formation? There will be formation of CH2 plus. That means carbocation formation took place. Now you can see this is your 1 degree carbocation. If you want to move this positive charge to the right hand side, it is not possible because there is no carbon on the right hand side. So this positive charge will move to the left hand side, because when you are going to do 1,2 hydride shift, I'm gonna do 1,2 hydride shift. As you can see, H negative will move from left to right. So if negative will be taken out from this carbon, there will be positive charge. And as you can see, negative will go to this C positive and it will make it neutral and it becomes CH3 because H negative goes and add up to them. So now you can see this is your 2 degree. Now since this carbocation is more stable, that means rearrangement will take place. Whenever you are going to do the rearrangement from one to another, another should be more stable than the first one. As you can see, this is your 1 degree carbocation and this is your 2 degree carbocation. That means 2 degree carbocation is more stable and hence the rearrangement will take place and then OH minus will come into play and then it will attack here and you will get propane 2-ol. Are you getting my point, everyone? Saf, Alan, Mamuna?
Yes,
sir.
sir.
Okay. I will give you a question. Are you able to send message now?
No, sir.
No. Today I'm not able to see also in the chat box. I don't know. Where is chat box? Can you see that? Let me wait a minute. Can I change the slide?
Yes, sir.
Okay. Just wait a minute. Okay. Now I'm gonna give you a question. First of all, I'm gonna give you a very easy question like this. OH is here, and you are going to react this with HCl in the presence of ZnCl. And the next question that I'm gonna give you is this. Just wait a minute. I'm gonna give you is this. OH is here, and you are going to react this with HCl in the presence of ZnCl. Please do this question. Any answer from anyone of you?
Sir, is it trimethyl trichlorine methyl?
Can you speak again? 3
3-methyl trichlorine pentane.
3 chloro we say, okay? 3 methyl you told me, 3 methyl, 3 chloropentane, right? Is
Yes,
it
sir.
for the last one or the first one? A or B?
The B1.
Okay, I'm going to explain. You will see, you will just match it. Okay, first of all, what you are going to do, just remove this OH. OH will be removed like this. So what will happen here? You can see there will be formation of carbocation. Okay, wait a minute. I'm going to explain the first one. It will be more easy to understand the second one with the help of the first one. Okay, now see. For the first one, as you can see, it will move like this. So there will be formation of carbocation. As you can see, this is your 1 degree. And if you are going to do, this is your 1 and this is your 2. That means 1, 2 hydride shift H shift. Then what will happen? Then you are going to move this charge to the positive. 2 degree it will be. If you are going to again move this charge to this carbon, it is also 2 degrees. So you are not going to do it. And then this OH minus will come into play and it will attack this and you will be getting OH. You can also do the next one. You will be getting 2 degree ethyl and it will be like this. This will be also the product. Is that clear? All you need to remember is which one will go through carbocation. Whenever carbocation formation takes place, then you can rearrange if possible. Now you will see this. This will move like this, and the rest part will be as it is. Now you can see if you are going to move this 1, 2 hydride shift, 1, 2 hydride shift, then what will happen? Then you can see this is your this was your 1 degree. Now this is your 2 degree. Now if you are going to move this 1, 2 hydride shift, what will happen? What will happen? This positive charge will come here, and you can see this is your 3 degree carbocation, and you know 3 degree carbocation is more stable. Then OH minus will come into play and it will attack here, and you will be getting this product. And its name is 3-methyl 3-fluoro. Sorry, OH is not there. I just made a mistake. Cl minus will come into play, not OH. OH was there already. Cl minus, Cl minus. So this 3-methyl 3-chloro pentane. Very good. Alan, have you got it?
Yes, sir.
Mamuna, can I change the slide?
Yes.
Okay. Now the next preparation you already know. Okay, I'm going to ask you a question. All of you are comfortable with the methods of preparation of haloalkane and haloarenes. If you know this, we are not going to waste our time. Just let me know if anyone have any doubt in methods of preparation of haloalkane and haloarenes. Does anyone have any doubt? No reply.
No, sir.
Alan, tell me. Mamuna, Aksha.
Yes.
I'm not getting it. If you are gonna say only yes, sir, no, sir. If you have doubt, if you don't have doubt regarding this methods of preparation, because you just studied it in class 12, so I hope you know. If you don't know, if you have any doubt, just let me know. I will teach that. But if you already know, then we are not gonna waste our time on the preparation of haloalkanes and haloarenes. What do you think, Mamuna? Uh, please answer me honestly. Mamuna, Aksa. Hiba, Farhad. Alan,
Yes, sir.
do you have any
No,
doubt?
no doubt, sir.
No doubt. Mamuna, please do respond. Yes. Do you
No,
have
sir.
doubt?
No, sir, I don't.
Actually, it will save some of our time. Then we will use that time in solving the previous year's question. That's why I'm asking. So can we directly move to the chemical reaction? Yes or no?
Yes, sir.
Okay. If you don't have any doubt, okay. So I'm gonna ask you some question. If I'm gonna give you a very simple question. Let me remove this part and make it a very simple. CH3, CH, double bond, CH2. And if you are going to react this with HBr, and if you are going to react this with HBr in peroxide, okay, and if you are going to react this Br2 in the presence of CCl4, please do let me know the name of the product. Any answer?
So the first one be CH3, CH2, CH2Br.
The first one, that means
With
this
peroxide.
one A.
Yes, sir.
Can you tell me the name? 1-bromopropane.
Yes, sir.
Okay, it's wrong. First of all, you are going to see this is your alkene, and if you are going to treat this with HBr only, then this is your Markovnikov. Markovnikov. And what is Markovnikov? Negative part will go to that carbon across double bond which has lesser number of hydrogen, and positive part to the carbon which has greater number of hydrogen. So the product will be this. Now you are going to see alkene with HBr in the presence of peroxide. Presence of peroxide. So you can see R2O2, that represents peroxide. That means it is anti-Markovnikov. Anti-Markovnikov. And what does anti-Markovnikov says? Negative part will go to that carbon which has greater number of hydrogen, and positive part will go to that carbon which has lesser number of hydrogen. So the product will be, now it becomes CH2, and here it will be CH2Br. So before doing any reaction, you have to recognize which type of reaction is there. Now, if you are going to react this Br2 in the presence of CCl4, this will be broken, and Br will be added to the adjacent halogen, adjacent carbon. So this will be the product. Isn't it easy?
Yes, sir.
Can I change the slide?
Yes, sir.
So I just covered the preparation of haloalkane from alkene. Now the next, if I'm gonna give you CH3, CH2, Cl, and you are going to react it with sodium iodide in the presence of dry acetate, what will be the product? And if you are going to react this with CH3Br with AgF, what will be the product?
The first one is 1-iodoethane.
Very good. Basically, halogen exchange will take place, right? Halogen exchange will take place. This both reaction comes in halogen exchange. What about the next? You can see fluorine will replace bromine, so it will be CH3F. Fluoromethane. It is fluoromethane. What is the name of the reaction? This is basically Finkelstein, in which we especially prepare iodoalkane, and to prepare especially fluoroalkane, this is known as Schwarz reaction. Schwarz reaction. Is that clear?
Yes, sir.
So I'm gonna change the slide. So I'm gonna write this physical properties. What it is? Physical properties of haloalkanes. So the first is they all are colorless. They all are colorless. The second, they are having sweet smell. The third, we can write polar. They are polar but insoluble in water. Insoluble in water. Generally, polar dissolves in polar, but they are insoluble in water. In spite, water is polar and they are also polar because no hydrogen bonding. Because of no hydrogen bonding, they are insoluble. Then comes your boiling point. Boiling point directly proportional to molecular weight. So RF will have the list, then chlorine, then bromine, and then iodine. Is that clear?
Yes, sir.
These are some physical properties. Now we are going for optical isomerism. Now we are going for optical isomerism. What is this optical isomerism? So basically, stereoisomers, these are part of stereoisomers. Stereoisomers, which cannot superimpose on each other due to chirality, and they are known as optically active or optical isomers. They are known as that isomers are known as optical isomers when the mirror image or they are not superimposable to each other due to chirality. So there is a term chiral. What is chiral carbon or chiral compound? So in any compound in which carbon should be sp3 hybridized, and the next condition is surrounded by four different group. Like if I'm gonna draw a chiral compound, so you can see CH, chlorine, CH3 and Br. So as you can see, this is sp3 hybridized and surrounded by four different groups. That's why this carbon is chiral. And whenever the compound is chiral, then generally it is optically active compound. And what is optically active compound? We will discuss about it. Is that clear? Chiral carbon?
Yes, sir.
Yes or no? Okay. Now I'm gonna give you some question regarding this. So can you tell me whether it is chiral or not? We are going to check only at halide position. Only you need to check the here.
The second one is chiral.
The first one is not chiral only because you can see there is a hydrogen. First of all, you are going to check the hybridization. It is sp3. This is different. This is different, but this is ethyl and this is also ethyl. Same. That's why it is not chiral. Achiral, we will say achiral. Now, if you are going to check it, this is your chiral. Sorry, this is your sp3. First of all, I'm gonna show you hydrogen. Hydrogen is there. Now, if you are going to check it, you can see this is your sp3. First of all, sp3, then surrounded with hydrogen, chlorine, methyl, and ethyl. That's why this compound is chiral. And if you are going to check this one, you can say this is your sp3. That is well and good. This bromine is different, chlorine. Here it is ethyl, and again here it is ethyl. So it is also a chiral. Is that clear? Is that clear? Yes or no?
Yes, sir.
Okay. Now moving to the next term that is very important. The term is basically inversion, retention, and racemization and racemization. What is inversion? So it's very simple. I'm gonna explain this with the help of an example. This is your chlorine, this is your CH3, this is your C2H5. So first of all, I'm gonna ask whether it is chiral compound or not. Is it chiral? Yes or no?
Yes, sir.
Yeah, it is chiral. Now there is a reaction, and that I'm gonna show you nucleophile, and there is another that is also nucleophile. Now see what will happen. First of all, if chlorine is gonna move from here, this nucleophile will attack. This nucleophile will attack, and there is a probability. Let me just write it: C2H5, and then comes your CH3, and then comes your nucleophile, and then hydrogen. There is another probability, that is carbon, and nucleophile is here, CH3 as it is, C2H5 as it is, and hydrogen as it is. Let's say this is your A and this is your B. And if you are going to react from here, nucleophile, you are getting A plus. See what happens here. In this reaction, on the left hand side, you can see nucleophile react with this reactant and just replaced chlorine where chlorine was. That means basically nucleophile just replaced the chlorine, and it is there where chlorine was. It is there where chlorine was. In whatever orientation chlorine was, nucleophile is there. This is called a retention. This is called the retention of configuration. That means chlorine just moved from its place and nucleophile just replaced that. But in the right hand side, you can see chlorine was on the left hand side, but the nucleophile is on the right hand side. That means it reversed its place. That's why this is known as inversion of configuration. This is known as inversion. And if you are going to do a reaction in which both have possibilities there, front attack as well as back attack. This is your front attack as well as this is your back attack. And if you are getting in equimolar, that means both same molar. So this type of mixture is known as racemic mixture. If you are getting both A and B, that means front attack or back attack, racemic mixture, and the process is known as racemization. Is that clear, everyone?
Yes, sir.
So it's very, very important. Can I change the slide? Okay. Now, the next reaction, the next topic is chemical reaction. Chemical reaction. And here we need to study about three type of chemical reaction. The first is nucleophilic substitution reaction. The second one is elimination. And the third one is reaction with matter. Reaction with matter. So I'm going to start this nucleophilic substitution reaction. Nucleophilic substitution reaction. This is of two types. You have heard of this. That is SN1, nucleophilic unimolecular substitution reaction, and the another is SN2, nucleophilic bimolecular nucleophilic reaction, you can say, or this is your unimolecular. So it's very simple. I'm going to write the name. So this has a name, unimolecular nucleophilic substitution reaction, and this is your bimolecular nucleophilic substitution reaction. First of all, you are going to write a point about this. SN1 is occurs in two-step reaction. Okay. The next point, very important. In two-step, first step, carbocation formation takes place. In the second step, nucleophile will attack. Nucleophile attacks. So it is two-step reaction. The second point, which is very important, it is first order reaction. It is. SN1 is first order reaction because rate is directly proportional to Rx, and you know the power is 1. That's why the order of the reaction is 1. Now the next is very important, and that is third one. Racemic mixture takes place. Racemic mixture occurs. Now I'm going to explain this how the reaction took place. Let's say this is your R, this is also your R, and this is also your R, and X is there. So in the first step, what will happen? This will move. Living groups live with the electron of carbon. So there will be formation of carbocation. And this is slow step. That's why rate determining step. This is your rate determining step. Now, if you are going to react, see, this is your first step. Now for the second step, then nucleophile will come, and either it can attack from front as well as back. That's why you will be able to get inversion and retention both. That's why racemic mixture you will get. Is that clear, everyone?
Yes.
Now the next point, which is very important, if you are going for reactivity, so as you can see, carbocation takes place. So 3 degree alkyl halide, then 2 degree alkyl halide, then 1 degree alkyl halide, and then comes your the next, that is CH3. So this is the reactivity of the alkyl halide. If you have the same alkyl group like Ri, Rbr, RCl, Rf. So in this, best living group is iodine. So this will be the reactivity order if alkyl group is same. Is that clear, everyone?
Yes, sir.
Can I change the slide?
Yes, sir.
Okay. If you are going for SN2, that means bimolecular nucleophilic substitution reaction. It is, first of all, it is single step reaction. Single step reaction. Single step reaction. The second point we can write, it is second order reaction. Second order reaction. The third point we can write for this, rate is directly proportional to nucleophile and alkyl halide, and you can see power is 1 and 1. So in rate of reaction, if you are going to add the power, you will get 2, and that's why it is second order reaction. And the fourth one is inversion of configuration takes place. Inversion of configuration takes place. Now, why inversion of configuration takes place? So I'm gonna explain with the help of an example. As you can see, there is C, X is there, R is there, R is there, and R is there. Single step reaction it is, and OH minus is there. OH minus is there. Now, if this will leave carbon with a carbon's electron, there will be negative charge, and this wants to attack here. But as you can see, this also has negative, this also has negative. So there will be repulsion, and front attack is not possible. Front attack is not possible. Why not possible? If you have studied chemical kinetics, so proper orientation should be there, and this is improper orientation. This is your improper orientation. See, in SN1, first X leaves with the carbon's electron. OH minus does not attack at the same time. X minus leaves the leaves its group with the carbon electrons. Then the formation of carbocation takes place. Then OH minus can come and attack from front as well as back. There was no steric hindrance, no repulsion. But since this is your single step reaction, at the same time this will be happening, but this is not possible. That's why OH minus will come and it will attack from back. It will attack from back. That's and you can see X minus is in front and OH is attacking from back. So OH will be on the back side and X was on the right hand side, and OH is on the left hand side now. That's why inversion takes place. So see how the reaction will take place. At the time of breaking of this bond, this bond is started formation, and then it goes and OH will come here. Now you can see OH is just opposite to the X. That's why it is inversion. So in SN2, inversion of configuration takes place. In SN1, racemization takes place, because in SN1, front attack as well as back attack both are possible. Is that clear? Now I'm going to talk about the reactivity. As you know, for SN2, these are steric hindrance, bulky group. So if it will be lesser, that means CH3X is the most reactive. Then comes your 1 degree Rx, then comes your 2 degree Rx, and then comes your 3 degree Rx. And if you go for Ri, RBr, it will be same, because best leaving group is iodine. OH minus will be attacking easily if hydrogen is there only, because it has a small size, so there will be no steric hindrance. Then 1 degree, then 2 degree, then 3 degree. Is that clear, everyone? Can you change the slide?
One minute, sir. Yes, sir, done.
Okay. The next is, just let me know which one will show react faster towards SN1. This is for SN2. Reactivity towards SN1 and SN2.
So what's the question?
Reactivity towards SN1. Reactivity. You need to tell me the reactivity of this A and B towards SN1 and this A and B towards SN2. Simple question. Alan, please do answer. Mamuna.
Yes.
Okay, see SN1 3 degree, 2 degree, 1 degree. So this is your 3 degree and this is your 2 degree. So this will be reacting faster. SN2 1 degree, 2 degree, 3 degree. So you can see this is your 1 degree, this is your 2 degree. So 1 degree will be faster in SN. Isn't it easy?
Yes, sir.
Can you change the slide?
Yes, sir.
Now see the elimination reaction. This elimination reaction is also known as beta elimination reaction, also known as dehydrohalogenation. Dehydrohalogenation. So as you can see, dehydrohalogenation, that means the removal of HX. Removal of HX. And this is also known as anti-elimination. What is anti-elimination? I will explain with the help of an example. Anti-elimination. So now you can see, if you have C, H like this, this is your X. This is your X. So as you can see, or you can remove this hydrogen if you want, not a problem. First of all, the carbon to which X is connected, this is your alpha, and the carbon which is connected to the alpha carbon, that is your beta. So you are going to remove X from alpha and H from beta. So it will be C double bond C. It will be like this. And this reaction will be taking place in the presence of alcoholic KOH. Is that clear? Is that clear? Yes or no?
Yes, sir.
Now, what I told you is it is anti-elimination. What does this mean? This means basically, if this is the scenario, if this is your scenario, hydrogen is there, and then comes your this hydrogen, and then comes your this hydrogen. Okay, and if you are going to make it like this, X, and this is your hydrogen, and this is your hydrogen like this. Now, I told you the reaction is anti-elimination. That means if you are removing X, which is solid waste, so you need to remove. You can see 3 alpha hydrogen, beta hydrogen you have, but you are going to remove that hydrogen which is opposite of this. So you can see this is what solid waste. So opposite of solid waste is dash waste. So you are going to remove this and you will be getting this product. Since here it won't affect whatever you are going to write, but you need to understand what is anti-elimination. Anti-elimination, that means if X is out of the plane, you are going to remove the hydrogen from beta carbon, which is inside the plane. Are you getting my point? Yes or no? Alan, Mamuna, Sir?
Yes, sir.
Yes, sir.
Please do that, you can let me know. Now see, if you are going for reactivity, again formation of carbocation takes place, and in here 3 degree Rx, then 2 degree Rx. Whenever formation of carbocation takes place, then 3 degree will be more reactive, and it since it is stable, that's why it is more reactive. Is that clear? Can I change the slide? Okay. Now see, preparation of halogens. Preparation of halogens. It's very simple. Halogens, preparation of halogens. So the first preparation is, this is also from electrophilic substitution reaction. From hydrocarbons by electrophilic substitution reaction. You know what is electrophilic substitution reaction? In the previous chapter, if you revise that, so as you can understand, this will be your electrophilic substitution reaction. Hydrocarbon, that means this is your toluene, which is hydrocarbon. And if you are going to react this with X2 in the presence of Lewis acid, like either FeCl3 or Fe, we can write FeCl3, you can also write Fe, or dark, that means low temperature. What will happen here? With the reaction of this reagent, you will be getting an electrophile, that is X plus. So this X plus will be attacking either at ortho or either at para. So with respect to CS3, the product will be like this. If CS3 is there, X will be at ortho, and if CS3 is there, X will be at para. Have you got it? Yes or no?
Yes, sir.
Okay. Can I change the slide?
Yes, sir.
The next is from Sandmeyer's reaction. This is a name reaction from Sandmeyer's reaction. Now, as you can see from Sandmeyer's reaction, we are going to react this aniline with nitrous acid. With nitrous acid, that means NaNH2 in the presence of HCl, NaNO2 in the presence of HCl, and the temperature should be 273 to 278 Kelvin. So, wait a minute, please. Oh, sorry, this is a start, and so let's put it. So from Sandmeyer's reaction, you are going to react this aniline with nitrous acid, then you will be getting a diazonium chloride, N2 plus Cl minus. This is the diazonium chloride. After getting this diazonium chloride, you are going to react this with Cu2X2, and then N2 will be removed, and you will be getting this chlorobenzene. And N2 will be released. This reaction is only valid for X is equal to chlorine and X is equal to bromine. For iodobenzene or chlorobenzene, we use different method. We will do that in amines also. So is that clear? This reaction is followed, happened in 2 steps. Is that clear?
Yes, sir.
No. So this was your what we say preparation of haloarenes. Now the next, which is very important, chemical properties. The first one was for haloalkane. Now we are going for haloarenes. Haloarenes. So in haloarenes, what happens? First of all, aryl halide, that means haloarene, aryl halides are extremely less reactive, towards nucleophilic substitution reaction. As you know, haloalkanes has nucleophilic substitution reaction, but when you are going to talk about this haloarenes or aryl halide, it is extremely less reactive towards nucleophilic substitution reaction, and only because of three main reasons. You can see this is your haloarene and this is your haloalkane. First of all, the first reason I'm gonna tell you is a resonance effect. Basically, the lone pair are in conjugation and there will be resonance. That's why this bond will have partial double bond character. But this doesn't have partial double bond character, pure single bond, so it will be easily breakable. The second is difference in hybridization. As you can see, the hybridization of this is sp2 and the hybridization of this is sp3. And the third, which is very important, if you are going to remove in any way, you are going to break this bond, remove the chlorine, so there will be formation of phenyl cation. Which is highly unstable. That's why haloarenes or aryl halide does not favor nucleophilic substitution reaction. If you want to do nucleophilic substitution reaction in haloarenes, then you are going to have a very drastic condition. That means temperature and pressure should be exceptionally very high. Is that clear? Can I change the slide?
Yes, sir.
Alan?
Yes, sir.
Okay. Now you can see I'm gonna do a nucleophilic substitution reaction on chlorobenzene, and you will see the condition. This is your chlorobenzene, and to do a nucleophilic substitution reaction, first you are going to react this with NaOH. That is okay, but the reaction should be at 623 Kelvin and 300 atm pressure. That means the temperature and pressure is very high, and then H plus. Okay, please do it. So as you can see, this is your drastic condition. That means temperature and pressure is very high, and then only this nucleophilic substitution reaction will take place. And this is also known as Dawes process. Is that clear? Please do write
Yes,
it.
sir.
Okay, now if you want to do this nucleophilic substitution reaction, you have to make this chlorobenzene more and more reactive. How we are going to do that? How we are going to increase the reactivity of this chlorobenzene? So we just need to add a group which shows minus M effect. Basically, as you can see, this is your chlorobenzene, which is plus M effect, which will increase the electron density in this benzene ring. So I'm going to add NO2, and NO2 has a tendency to withdraw electron. That will decrease the electron density in benzene ring and make it a slightly more reactive. So you can see the drastic condition changes. You can see initially it needed 623 Kelvin, but by adding NO2, you will be needing only 443 Kelvin, followed by acidification, and then you will get this. Then you will get this easily, more than the previous one. Now, if you are going to add two NO2 group, it will be more, very more reactive than this one. So it will be like this. You can see NO2 is there. It makes more reactive, and you can see the condition is NaOH. You are going to add NaOH at 368 Kelvin. That means lesser than 100 degrees centigrade it comes, followed by acidification. Then you will be getting this product. Then you will be getting this product. And again, oh wait a minute, this is not chlorine. This is NO2. This product. Now, if you are going to add 3 NO2 to this chlorobenzene, if you are going to add 3 NO2 to this chlorobenzene, then it is so reactive that even warm water will work on that. This is your chlorine. Warm water will work on that, and this chlorine will be replaced by a nucleophile, which is OH, hydroxy. So the most important point in here is that if you are going to react directly chlorobenzene with NaOH in the presence of H+, you need high drastic condition like high temperature and pressure. And if you want to do it a lower condition, then you need to make this reactive. And how you are going to do that? You need to add NO2 or minus M group. Is that clear? Can I change the slide?
Yes, sir.
Do you remember in the previous class we did electrophilic substitution reaction? If you remember, do you remember that? Yes or no? See, if I'm gonna give you a question like this, chlorobenzene is here, and you are going to first react this with, I will say, and then again react this. I'll tell you with what you need to react, and then you are going to react this. Okay. Now, the first is you are going to react it with X2 in the presence of either AlCl3, or you can use X2 plus FeCl3. Then the next reaction I'm going to give you is HNO3 in the presence of H2SO. The next reaction I'm going to give you is either H2SO4 or oleum. And this is in presence of SO3, fuming H2SO4 we say, or either we can do this RX in the presence of AlCl3, or either you can do this RC double bond OX in the presence of AlCl3. If you remember this, wait a minute. This reagent will react with each other and form an electrophile, which is X plus. And wait a minute, X plus. Okay, this is also X plus. Okay, it's okay. X plus. You can take X as well. X. So this, if I'm gonna take Cl2, it will be more easy to understand. Cl2, you can see Cl2. So there will be formation of an electrophile, which is Cl plus, So what will happen? This Cl plus will be attacking at two positions. One is ortho and another is para. Yes or no? Saifullah, this will be your major and this will be your minor. Again, from this, you know this, there will be formation of nitronium ion NO2 plus, and it will be attacking. It will be attacking at two positions. One is ortho, and another is another is para. If you are going to see this, there will be formation of SO3H, which will be attacking either on ortho and another will be at para. You can see there will be formation of what? R plus, there will be formation of what? RC double bond O. So I'm gonna write it like this. Cl is there, R is at ortho, Cl is there, R is at para. Now you can see this reaction as well. Cl is there. Now C double bond O, R is there. Now the another one is this Cl, and this is your C double bond O, R is there. So you just need to remember the name as well. You know, this is your, the first one, chlorine. This is your halogenation that we already done. This is your nitration. This is your sulfonation. This is your Friedel-Crafts alkylation. And the last one is Friedel-Crafts acylation, if you remember. Yes or no? So only the reaction that I have left is reaction with metal that we will discuss in the next